For our first example in 4.2, I'm going to do number 1, and then we're going to do number 2. So what I have is, for the following exercises, identify if the given statement represents an exponential function. So I want to see how things are changing. If things are changing at a regular rate, then it's going to be a basic linear function. If things are changing proportionally, or by a factor, or by a percentage, it's going to be an exponential function. So this says after the initial membership cost of $10. So I have to pay $10 regardless. Okay. So my function is going to be, I've got to pay $10. Okay. The cost to purchase any audiobook from a certain company is $2.99. So I can do $2.99 times however many books I am purchasing. So if I purchase one book, it's going to be 10 plus $2.99 is $12.99. Okay. If I purchase 2 books, it's going to be my original 10 plus $2.99 times $2.99, or plus $2.99 plus $2.99, because I've got $2.99 times 2. So that's going to give me an answer of $5.98. Okay. So $15.98. So this is going to be a linear function, and this is a constant growth. Okay, so it doesn't matter if I buy 100 books or if I buy 1 book. It's going to cost me $2.99 per audio book. It is a constant change. The second one says a population of bacteria increases by a factor of 1/8 every 24 hours. So I don't even need to know the initial population. I know that I start with 100%. Okay. After an hour, I have 100% plus 1/8 of that. After another hour, I have 100% plus 1/8 of that. Okay. So I end up having this model where I'm going to write it as an exponential function. So how much do I start with? I'm going to start with 1, which is 100%. And that's going to increase by 1 point. Well, I need to know what 1/8 is. So on your calculator, I have 1/8. Oops, sorry, that's 18. 1/8 is 0.125. So I've got my initial 100% times 1.125. And then whatever I have here, if this is 1 hour, 2 hours, 3 hours, 4 hours, so this is my exponent. This is going to be exponential because it is not a constant rate of change. So I've got a growth rate of 1/8, but that's going to change every hour, okay, based on my initial amount. So that is exponential. All right, so reading the next one. The population of India since 2013 can be represented by the following exponential model, where the population, in terms of time, equals 1.25 times 1.012 raised to the t power. This is exponential. My variable is in my exponent. This is an exponential model. Is this growth or decay? So let's look at the growth rate. My growth rate is more than 1. So therefore this is growing. Okay, this is not decay. This is growing. If it was less than 1, because the 1 stands for 100%. So I've got the 100% plus an additional 1.2%. Okay, so this is growing. If it was decaying, then this amount right here would be between 0 and 1, but not include 0 or 1. So it would be a fractional amount. So this represents growth. What does that mean in the exponential model? It means that this is growing by 1.2% every year. It's growing by 1.2% every year. So where did I get the 1.2? Because what I have first is 1, and I can add that this way. So this is my 100%, which means I moved my decimal twice to the right. So now I need to move my decimal twice to the right to be in percentage. So I have my initial 100%, and I'm adding 1.2% every year. Okay. What is the growth or decay rate? I just told you. It is 1.2%. I have my initial amount, but it's growing by 1.2%. In the exponential model, that is this amount. Okay. If P of T, or if your population is in billions, what's your initial population? So if I look at my initial value, the population in terms of time is 1.25 times 1.012 raised to the T exponent. This T, if it were 0, meaning my year 0 or 2013, any number to the 0 power is 1. So 1 times 1.25 is my initial population. And in billions, that means I've got 1.25 billion people in India in 2013, which would be 1,250,000,000. Oops, sorry. 1,250,000,000. Okay, that's how many people were in India in 2013.